chapter 10 today. We're doing RC circuits, and we got a pretty good start on them last week. So I feel we can definitely wrap this up today. Um, we'll probably have time to do a few homework problems. So if there's any homework problems that seem interesting, be sure to let me know. Um, and I think that's all I have to say. Oh, the Chapter 10 Expert TA due this Friday, and there'll be a quiz over the weekend on Chapter 10, just Chapter 10. Okay, shall we get started? Okay, I forget exactly, no, I need to share it, sorry. I forget exactly how far we got. Like, I don't think we had started doing math, but I do think we had drawn just like a ton of graphs and talked about what we expected to see. Maybe even like written down the Kirchhoff loop. Does that sound familiar? Okay, so like 2 minute recap. Okay, okay, it's okay. Okay, there we go. 2 minute recap. We have this circuit with a switch in it that will hook up to a capacitor, and not that way, a capacitor and a resistor. How am I going to do this? And a resistor. Man, resistor. Ha! Excellent. I'm going to call that R. And now we're gonna start with the charging, and we'll move on to the discharging after we get the charging done. But the idea is initially this capacitor is uncharged, and then you flip the switch, and current starts going through the circuit. But as current goes through the circuit, starts charge building up on the capacitor, where the more charge that builds up on this capacitor, the less current is able to go. And so you have this iterative process here that as more charge builds up, less current can go, but as long as the current is positive, charge will still build up, so the current will decrease, and so you get this exponential decay on the current. And you get something very similar but opposite for the capacitor, where charge starts building up quickly at first because the current's high, so lots of charge gets deposited. But once there's a certain, once the charge is built up, then the current has slowed down, so charge keeps building up because you still have current, but it doesn't build up as fast. But even a little more building up means that a little more current flows, a little more charge gets built up. So so the charge gets built up on the capacitor, charging the capacitor, but it kind of exponentially approaches this limit, this asymptote here, which you reach when your voltage across the capacitor has reached the voltage of the battery, because that's how much you can charge this capacitor hooked up to this particular battery. And at that point, the charge on the capacitor is the capacitance times the battery voltage, or the voltage of the capacitor that is equal to the battery voltage. Okay, this all seem kind of familiar? Okay. Then I hopefully said something like, we want to find an equation for charge with respect to time and current with respect to time that matches these graphs over here. To do that, we will write down a Kirchhoff loop for this circuit. So I close this circuit, our current starts going around that way. We go around this loop like that. So as we go around the loop, we hit, we'll start right there. We go through the battery, where we're going from negative to positive, so we have a positive battery voltage. So plus E. Then we hit this capacitor, and we're going from the positive side of the capacitor to the negative side of the capacitor. So this works very much like the battery, where when we went from negative to positive on the battery, we got a plus voltage. When we went from positive to negative, we got a negative voltage. Here we're going from positive to negative, so our voltage is going to drop across the capacitor. Then we hit the resistor. We're going with the current across the resistor. So we're going to have a voltage drop across the resistor. Then we come back around to where we started. So we say the whole thing adds up to 0. Okay, and I think this was about where we stopped last time. Okay. Okay, so this is like writing down an energy conservation equation. Mainly, we're just writing down something we know that has everything included, so we can solve for the thing we want. Kirchhoff loop is useful for that because I know that when I go around the loop, I can write down something about each component and add it up to 0. It's just a way to generate an equation. However, we want charge and current with respect to time, and right now I have voltages, so I need to plug into things here so that instead of voltages, I have current and charge. So like starting with the voltage across the resistor is in an equation that involves voltage, resistance, and current that maybe we can make a substitution in. V equals IR. So here I will have IR. For the capacitor, the voltage across the capacitor, you can't relate that to current, but you can relate that to charge via this equation, where the voltage across the capacitor will equal the capacitance multiply, will equal the, sorry, let me do it on the next page. C equals Q over V. So the voltage on the capacitor will equal whatever charge is on the capacitor divided by the capacitance of the capacitor. So I'm going to create Q cap over C. There's my EMF. Okay. Now this is better because we're down to 2 unknowns, because we know the EMF, we know the battery, we know the capacitor, we know the resistor. Those are all things that we can put into the circuit ourselves. But the current and the charge we don't know. So we still have 2 unknowns in one equation. So it would be nice if we could make some sort of substitution involving charge and current. So is there an equation that relates charge and current? There's a better one. Yeah, that is exactly it. Where current was, it's change in charge over change in time, or if you wanted to do calculus, derivative of charge with respect to time. So we are getting really close to where we need to be here. I'm going to stop writing capacitor Q sub cap, and I'm just going to start writing Q because I'm never going to be able to keep that up this entire time. So let's just know that should always be faster, and I'll bring it back when I'm done getting through here. Okay. Okay, this is delightful. This is a great equation. We're down to one equation, one unknown, and we got to solve it. And we will solve it the same way we solved the air resistance equation that we got last semester, where there's actually a little bit that you guys are going to get to do on the homework. Kind of walks you through this process. The last couple of problems in the homework kind of walk you through this whole solving a differential equation. But the way we're going to solve this differential equation, we're going to get everything with the q on one side. We're going to get everything with the t on the other, and then we'll be able to integrate both sides. Okay. Okay, so since I know where I'm going, it gets a little bit easier. So here are the steps I'm going to take. I'm going to move this to over here. And so I'll have the battery EMF minus Q over C equals dQ dt times R. I'm going to divide both sides by R. Like that. And so I will have dQ dt equals EMF over R minus Q over RC. That RC is going to become important in a minute. Next thing, I'm going to find a common denominator here. Well, and I won't do it like that. I'll do it like that. We'll multiply that by C over C. And the idea there is I'm trying to combine a whole bunch of constants with my Q's. So I'm about to divide by CE minus Q. And so that'll get rid of all the Q's on one side, right? And then I'll multiply both sides by dt, and that'll get my dt on the other side. I also know that I wanted an R times the resistance times the capacitance, because I know that's going to come up in a little bit. So I'm just going to combine it right there. And I'm also looking at that capacitance times the battery voltage. And I'm saying, well, I know like the asymptote that I'm approaching is that battery voltage times the capacitance. And so I'm kind of glad to see this familiar term that's probably going to be in my final equation. So far, so good. Okay. So on one side, I'm going to have dq over CE minus Q. On the other side, I'm going to have dt over RC. Now there's a few more things that I'm gonna throw in here. One, looking at my equations here, I don't want an e to the positive anything. Like I don't want a positive exponential. I want an e to the negative variable, because I want things to decay over time. I don't want to zoom off to infinity. I want to keep things nice and calm. And that will be useful if I can get my dt to be negative, because I want as time progresses my function to get smaller. So I'd like a minus sign associated with my t. So I will do that. On one side of the equation, that means I'll have q minus CE. On the other side, I have dt over RC with a minus sign in front. And not that we couldn't have gotten there at the end, but it makes it easier to set it up with kind of the end in mind. All right. The equation is separated. I got all my Q's on one side, all my T's on the other. And so now all I have to do is integrate. Let's integrate the left-hand side first because it is easier. So left-hand side, right? That's the right-hand side. Yeah, that's the right-hand side. Right-hand side first. Sorry. The resistor and the capacitance, are those constants or variables? R and C. Constant, because as I'm, hook this up to a battery, I don't expect my resistor to change. I'm also going to pull that minus sign out. Okay, so I'm just integrating dt. And what is the integral of dt? Very good. And we should put some bounds on this thing. So we need to put like a start and a finish. So what's a good place to start the time? 0. So we hit go on our stopwatch. 0 is a good time. And I don't have like a good time to finish, so I'll just put in like a placeholder. We'll finish at some time t. All right, that gives me that for the right-hand side, I have negative t over RC. Right-hand side. Okay, now let's do the left-hand side. Left-hand side. Okay, so the left-hand side, I have dq q minus battery voltage times capacitance. And I hope that you guys are seeing like the dq over q thing that's going on. But we definitely have these constants running around, and I always have to do the steps. So we'll do a u substitution, where u equals q minus battery times capacitance, which means du will equal dq. And what about that battery and capacitance? Are those constants or variables? Constant. So they're not going to show up. So that's actually a pretty nice substitution there. I have du over u. And what is the integral of du over u? It is the natural log. It is absolutely the natural log, which is really great because we want to see an exponential in a minute, right? And so I know like an exponential and natural logs are inverses, so I can see it coming. However, just like with my time, I do want to put some limits on this. So first, let's switch back over to the units we have that we understand. And second, since we always put unit limits over here, 0 to t, we have to match those on the other side. So at time equals 0. So okay, so let's go through. We're integrating q. So q is our variable. At time equals 0, what's the charge on my capacitor? Say again? Okay. Initially, when I hook up my capacitor, is it going to be charged or uncharged? Uncharged. So the charge on it would be 0. Does that make sense? Because only over time is that charge going to build up. So we're starting at 0, and then over time the charge builds up. So sometime later it'll have some charge q on it that corresponds to this time t. So that q, that will be q with respect to t. Okie dokie. Plugging these in, I get q minus battery times capacitance minus the natural log of 0 minus EC. So that's just negative EC. And you should be looking at this and you should be saying this is, I feel like there's a identity. And so this is similar to the identity of natural log of A minus the natural log of B. And what is the natural log of A minus the natural log of B? A over B? A over B. Okay. So that means that this simplifies to the natural log of Q minus EC over negative EC. Okay, looking great. Looking good. All right, and there's the left-hand side. Sound okay? Okay, so we're done with calculus. We did the integration. Now we just have to set these two things equal to each other and solve for an equation of charge with one side and time on the other. So charge with respect to time. Let me copy this over. So I have that. I have a minus sign. On the other side, I'm going to have a negative T over RC. Okay, so I need the Q by itself on one side and everything else on the other side. So I need to get rid of that natural log. And how do you get rid of natural logs? E. Excellent. So I say if the natural log of that equals that, then e to that equals e to that. So we have Q minus EC over negative EC. I have e to the negative T over RC. We will multiply both sides by negative EC, and then we'll add EC to both sides. So I'll end up with Q equals minus EC, which is the battery voltage times the capacitance, times e to the negative T over RC, plus EC out front. And of course, we could write this a little bit neater. We could say Q equals this EC 1 minus e to the negative T over RC. Okay. Math-wise, how are we doing? Hey, confidence, I like it. If that makes sense, let's start looking at this equation and talking about what each part means. So for example, the battery voltage times the capacitance. We ran into that earlier, right? Back on the first slide, the battery voltage times the capacitance was the maximum charge that we were going to hit. So that C, E times C, that's the, what you might want to say is the Q max. Sound okay? The other thing is this RC. Now let me ask you, just by looking at this this equation, can you tell me what the units of RC would be? And one thing you might ask yourself, I have the exponent raised to something. Overall, what do the units need to be when you raise that exponent to it? I kind of hope that you guys are saying, well, they need to be unitless. It needs to just be a 1 or a 2 or a 0.3. Because it does. So this thing overall does not have units, right? So any unit you put in there, it physically wouldn't make a lot of sense. Like, I mean, mathematically, yeah, you could punch it into your calculator, but physically, there's no dimensions to this. Kind of like you wouldn't expect sine to have a dimension. Okay, so if there's no dimensions in this exponent, and I have a time divided by RC, what do the units of RC have to be? Yeah, overall, this thing has to be unitless. It better be time. And it is. So the units of RC, so we call RC a time constant. It's got units of seconds. And you usually just refer to it with a Greek letter tau, where what that tells you is that tells you how steep or shallow your exponential is going to be. So this is, whether you have a curve that looks like this or a curve that looks like this. Like, how quickly is that capacitor going to charge? Now, does that kind of make sense? Yes.
So like the units for this zone, the units for capacitance at
Farads.
How does that cancel out?
All right. Okay. So RC. Okay. These are ohms and farads. And so let's break that down. So like V equals IR. So an ohm has to be a volt per an amp, right? Okay. So we have a volt per an amp. My capacitor is charge over volts. Okay, so my capacitor is charge over volts. So that has to be a coulomb per volt. Okay, coulomb per volt. Okay, nicely enough, my volts are canceling out. And then we have this amp. That was a current, right? And a current is a charge per time. Yeah, see, it's all coming, right? So I have coulombs over coulombs per second. Coulombs per second. So yeah, those cancel out. Your seconds jump to the top.
I forgot that current is.
Man, for this one, I have to go through it every time because I'm just like, I don't know, it gets there. I know it gets there. Okay. Okay, so that time constant, the R times the C tells you how quickly you're charging that capacitor. Okay, so my capacitor is uncharged right now. Let's see how well this works. And so right now I have 1 light bulb's worth of resistance hooked up to my 1 farad capacitor. Maybe I can do 2 things at once. Okay, can you guys see this? Okay. Wow, these alligator clips are not super hefty. Okay, and so we're going to kind of just keep an internal tempo here of how long this takes to dim. And what we're looking for is not like a maximum brightness, but we're saying, okay, how quickly did that dim off? Does that make sense? Okay. Let me discharge it. Because now when I double this resistance by putting these 2 bulbs in series, what's going to happen? Now, will when I initially hook this up, will it be as bright as it was before? Okay, so I'm starting at a slightly lower point in terms of current. But what I want you to pay attention to is how long it takes to change. So how long does this take to dim? So I'm starting at a lower point, but is it really dying off as quickly as it did before? And I'm kind of hoping what you guys see is that it takes a longer time to get to this point as it did before. Yes, no, maybe? Okay.
Why is it even dimming in the first place? It has constant power from the battery.
So because we're building up charge on here. So let me go to this current. So the current goes to the wire, hits the battery, and it builds up charge on the battery, on the capacitor. Right, yeah, so yeah, as it's going through, it hits this capacitor, it builds up charge on the capacitor, which means that there's a voltage opposing it. And so that's just like putting a battery opposing my other battery. And that second battery gets a bigger and bigger voltage, and at some point it's big enough to block the current altogether. Okay. When I added the second resistor in series, these are identical resistors. When I added the second resistors in series, what happened to the total resistance of this circuit? Now it increased, but do you guys know by how much? Factor 2. So I doubled the resistance. What happened to the time constant then? The tau. Yeah, so basically I doubled my time constant by adding another resistor in series. Okay. Now, okay, so we have this idea, we have this thing, this is Q max out front. We have a time constant, so that tells how steep or shallow this curve is. We should, of course, kind of look at this and say, does this actually match the shape that we thought we should get? So here's the shape that we thought we should get, which it really is 1 minus e to the negative t times some constants. Because basically, think about, you're taking this, that's the 1, and you're subtracting off that. That's the e. Does that make sense? So it should just look inverted from your e to the negative x. Okay, I got some nods. Okay, so not only does this equation, do we understand it? It definitely makes sense to what we had, what we thought in the beginning. And it does match up with what we're seeing over here, but it won't be as obvious until we figure out the current, because really when you're looking at the brightness of the bulb, what you're doing is measuring the current. So it would behoove us at this point to derive the current with respect to time. And so if you have an equation for charge with respect to time and you want to find the current with respect to time, how might you do that? Just take the derivative. Straightforward, right? Okay, so I is dq dt, and q is EC 1 minus e to the negative t, and I'm just going to have t over tau at this point, so I can write fewer letters. We'll split that into two derivatives to make my life easier. So we take the derivative of the EC, and then we take the derivative of EC e to the negative t over tau. What's this first derivative? That's the battery voltage times the capacitance. 0, because they're constants, right? Excellent. And since they're constants, we can pull them outside of this derivative, and we're just taking the derivative of e to the negative t over tau. What is the derivative of an exponential? Excellent. Itself times the derivative of the inside, right? And I'm going to write it out as RC at this point. Because the derivative of the inside here is going to be negative 1 over RC. Okay, so first off, my minus signs go away. And so I have EC over RC, e to the negative t over tau. I brought my tau back. And let's look at that. So clearly my C's are going to cancel. So those capacitances cancel out. What does the E represent again? It was the battery voltage, right? But yeah, so that's a voltage. So I have a voltage over resistance. What is a voltage over a resistance? Current. So this E over R represents the battery voltage. So like the biggest voltage we're going to see across the circuit divided by the resistor. And so that's the maximum current that we're going to see. So I'll write it. Current battery voltage over resistance e to the negative t over tau, where this thing is the maximum current. Okay, and so looking at this, I think this equation is a lot easier to tell that it matches up with this graph, because this is just an exponential decay, right? So my exponential decay, where we start off at the voltage over the resistor, or I max, and we die off over time. Tau is still equal to RC, which of course is still the time constant, and still tells you just how quickly you're going to gain or lose voltage across this capacitor. And this one's a little this one's a little easier to say it's experimentally verified, because the brightness of this bulb is directly proportional to the current going through that bulb. So when I hook this up, you can say we start off high and we die off over time. And then when you reach, as time gets really large, you notice it spends a lot of time just being dim. And so it's lingering, right? It never truly reaches zero. And in fact, it's hard for you guys to see out there, but even as you get really close to zero, if you stare at it very closely, you can kind of see a slight glow. So it definitely does exactly what that graph says it should. Okay, does that make sense? Okay, if that makes sense, I would like to go ahead and do a homework problem, if that's okay. Where the homework problem I want to look at is number 25. So just so you know, in your homework, I assigned you all of the problems, but there's several problems that look at RC circuits, and they kind of walk you through the exact math that we just did. So like number 24, not number 24, but number 23 is what we just did. It just walks you through step by step, charging a capacitor. They do the discharge too, and we'll talk about the discharge. I don't think we're going to do the whole thing, but we'll talk about it. But one thing I particularly like is that on number 25, they go through and they talk about the energy in a charging RC circuit. So we're kind of looking at the energy considerations here and where we think the energy is at any point in time. And so they have a slightly different RC circuit. I mean, it's the same thing. We have a resistor and a capacitor hooked up in series. So just a slightly different arrangement than what we discussed. A, B, C, R. They set the current that way. Okay, so they want to talk about when we're charging. So the same thing we've been talking about. So the initial voltage on the capacitor is 0. The initial charge on the capacitor is 0. And over time, we expect them to do things like this. So we're going to hook up like that. Okay. Given that, part A, they just want the equation of charge with respect to time. And so we're just going to write down what we just solved. Because they use V naught for the battery instead of E, instead of C times E, we're going to have C times V naught. But it's the same equation that we had. So no surprises there. Next, they ask for the maximum value of the current during however long you hook this up. So you have the situation where your capacitor is fully uncharged. You go to hook it up. When is the current going to be the highest? In the beginning or at the end? At the beginning. Awesome. Where the charge on the capacitor is 0, there's no voltage on the capacitor. And so this just looks like a resistor and a battery. So that means just like we said before, the maximum current would just be the battery voltage divided by the resistor. Sound okay? So Imax, battery voltage divided by the resistor. Okay. Then they want the current through the circuit with respect to time. And we do it just the way we just did this problem, where if we're given the charge with respect to time, we'll just take the time derivative, find the current with respect to time. And we'd end up here. I'm writing this down because we're getting to a point, I promise, where I have Imax e to the negative t over tau. So we had Imax e to the negative t over tau, just in terms of what they want us to talk about. Now that we have that, now they want to figure out the power consumption in the resistor as a function of time. Resistor with respect to time. Okay, first, let's talk about power consumption. Is my resistor generating energy or taking energy away from the circuit? Very good. I'm glad we agree on this. Like in this terms, it's the light of the light bulb, right? It's leaving the wires and reaching your eyes. So it's clearly leaving. So that's what we mean by power consumption. We want to think of power generation of a resistor. We would just think of power consumption. Okay, next. How might we find the power consumption of the resistor? What equations do we have that includes resistors and power?
Power being volts or
So power being watts. And so if you remember, we had a few equations for power. Because power was like a combination of current and voltage. And so looking at these three options we have, which one matches our needs best? If I want to think about the power through that resistor,
first one?
it's not a bad idea, but I don't have an equation for voltage yet.
Also, the last one.
The last one, because yeah, I have an equation for current. I know the resistance, so we will just take this and we will say I squared times R. And so so we have I max squared times R multiplied, and we're just going to have an extra 2 in our exponent, like that. That look okay? Okay. You should kind of see that this is like the maximum power that's going to be consumed by that resistor. So that's the power that resistor is eating right when you turn it on. But over time, that's going to die off as the current dies off. But this problem wanted to talk about the energy, not the power. And so the next thing we're going to do is we're going to start talking about how could I figure out the energy that's being eaten by the resistor. And for that, we're going to remember that power is change in energy over change in time, the rate at which energy gets used. Or you can even, of course, say the time derivative of energy. Which, of course, means that we can also do a calculus thing where if power is the time derivative of energy, energy is the time integral of power. So if I want to know how much power is being emitted by this light bulb over time, I could just, I know how much energy total is being emitted by this light bulb. I would integrate the power over whatever time I have. Okay. So energy. Since we're integrating power, we'll just take whatever we have for power and plug it in. I max squared R e to the negative 2t over tau dt. We definitely need to put some limits on this integral. So I want to discuss this scenario where we turn the circuit on, we flip the switch, and then we watch the battery run, we watch the current run. Is that current ever going to truly reach zero? No, right? So if I really want to know the total energy emitted, I have to start at time equals 0, and I have to go out to infinity. So my bounds are going to be 0, not to 8, but to infinity, sideways. Look good so far? This is part E right there. So there's E. Now we're actually going to integrate this. Sorry. Oh yeah, there we go. Now we're, yes, sorry, I lost my place. But yes, we are actually going to integrate this. So let's start looking at it. This Imax and this resistance, constants are variables. Constants. Then I'm integrating e to the negative 2t over tau dt. And so I'm going to do a u substitution where u will be negative 2t over tau. What's tau again, guys? RC, excellent. And though those constants are variables. Constants. Okay, that makes this really easy because then my du will just be negative 2 over tau. dt, sorry, dt of course. And flipping that around, my dt will be negative tau over 2 du. Okay, making those substitutions. Imax squared are, you can even just keep your limits, they're not going to change. E to the u du, and I need to multiply this whole thing by a negative tau over 2 e to the u du. Okay, I got that. That looks good. What is the integral of e to the u?
Just e to the u.
Just e to the u. Okay. Nice and easy. Over 2 times tau. We're totally going to throw an RC back in here at the end of the day. Just so you know. Okay, e to the u. Let us go ahead and switch our units back to this guy over here. So I have negative Imax squared times r times tau over 2, 0 to infinity, e to the negative 2t over tau. 2t over tau. Okay. Imax squared, r tau, 2. I think I got everything. Okay. Hopefully it's about to come together. Let's evaluate this. This guy. I have e to the negative infinity minus e to the negative 0. What's e to the negative infinity? It was what? Nope, 0. Excellent. So that's 0. What's e to the 0? Just 1. Okay. This is 1. That is convenient. These were nice limits. So I have negative 1 like that. My minus signs cancel, which is great. And now let's see what we can do in terms of getting all these constants to form something that makes sense. So I have an Imax squared. So I'll have an Imax times Imax. I have an R. I have a tau, which is RC. So one thing I might do is I might note that I have like current times resistance. And what is current times resistance? Voltage. Okay, so I have like, and that's the maximum current times the resistance. So that's the battery voltage there. And I've got 2 of them, right? I got 2 Imaxes and 2 Rs. So this is really 2 battery voltages. And I'm multiplying that by a C. Does this at all look familiar?
capacitor or?
Yeah, so we came across this, or at least something that looked like this in our capacitor chapter, where the energy in a capacitor was equal to Q squared over 2C and 1/2 QV and 1/2 CV squared. So we plugged in a bunch of different stuff and said any of these works. And I'm hoping that you see that that's what we got. So that's the power burned by the resistor. That would be equal to a fully charged capacitance. So this is 1/2 CV naught squared, where that's the battery voltage. That's how much energy this capacitor would have when it's fully charged. Okay. And so I kind of want. I'm gonna do this two ways. We're going to, so when we're charging this capacitor, just as much energy goes into the capacitor to make it fully charged as it does when it gets, as the bulb burns off. And we are about to look at the discharging portion, where, oops, you'll notice that the discharging portion of this, when I pull off all the charge through this capacitor and run it through the bulb again, looks pretty much exactly the same. If we give this a second, it'll dim out just like before. It starts at about the same brightness. And so when we're about to do the discharging, what I want you to kind of pay attention to is we can talk about the energy considerations of this, where the battery is dumping part of its energy into the capacitor and part of its energy out through the light bulb. But even more than that, when this capacitor is fully charged, it has the same amount of energy that this light bulb is giving off. So the energy is starting here and going directly out of the light bulb. So you can definitely think about this whole thing in a very energy conservation sort of way. Does that make sense? You can even do like the whole differential equation we did, but you're starting at a conservation of energy equation instead of a Kirchhoff loop, if you prefer. Okay, but does that all make sense? Okay. Okay, I'd like to wrap up RC circuits by talking about discharging. So a discharging capacitor, RC circuit. And so this was the charging RC circuit. Let me get rid of a whole bunch of stuff here. To discharge it, you do exactly like what we've been doing here. We're saying, okay, let's take the battery out of the equation here, where if instead of hooking up over there, let's hook up over there, and now we just have a fully charged capacitor hooked up to a resistor. One thing to note, I didn't do it, I'm probably not going to stick to it, is that your charging resistor might not be the same as your discharging resistor. So while your charging time constant might be R1 times C, your discharging time constant might be R2 times C. So make sure when you're plugging in for your resistor, you plug in the correct resistance. Does that make sense? Okay. Okay. Now, my discharging circuit. So I have a capacitor, I have a resistor. I don't have a battery. No battery. Capacitor, resistor, excellent. Looks pretty good. Capacitor. I'm just going to set a few things. I'll say the current goes around like this, and we're going to form our loop like that. Sound okay? Now, again, I want to find an equation of charge with respect to time and of current with respect to time. And so we're going to start with defining our Kirchhoff loop so we have an equation that relates everything. When I go across my capacitor, if I'm going from positive to negative, I'll have a negative voltage across my capacitor. If I'm going through my resistor with the current, negative voltage across there. And that'll take me all the way around. There's not much else. Adds up to 0. Okay, is that all right? And we'll make the same substitutions as before. The voltage across the resistor will be the current times resistance. The voltage across the capacitor will be Q over C. And then we'll say that the current is the time derivative of charge. dq dt times R. Okay. And at this point in our scenario, we would start separating the variables, integrating both sides, plugging in the limits, and solving for Q with respect to T. We are going to approach this a slightly different way, at which we are going to guess the answer, write down an equation for it, and then plug it into this equation and see if it works. Sound okay? This is a good solution if you're a physicist, because if you're a physicist, there's only 2 or 3 equations you ever want to be the right answer. Like, you don't want a crazy complicated equation. You want an equation, a nice simple one. And so it's always nice to say, well, you know what, why don't I just guess the simple equation and see if that works? Okay, so to properly guess, let's start thinking about what it would look like. So first off, current with respect to time. If I'm discharging the capacitor, that's like the brightness of this bulb when I don't have the battery yet. Let me charge up my capacitor really quick. Okay, so the brightness of this bulb with respect to time, it was not fully charged, but that's okay. Does it start high and go low, or start low and go high? Let's go over it one more time. Ignore this part while I charge my capacitor. But I'm about to hook up just my light bulb to my capacitor, and I'd like to know if it's bright at first then dims, or if it's dim at first and then gets brighter. So is my current going high to low or low to high? High to low, got it. Like that, right? So for my current, I expect an equation where I have like a maximum current and like a negative T, and just because we just did all that discharging, I'm betting I have a negative T over tau. Okay, what about the charge on my capacitor? So as this capacitor is discharging, do you expect that it's collecting charge on its plates or losing charge on its plates? Losing, right? Because it collected all the charge in the charging portion, and now we're discharging. So we're starting with charge, and then we're losing it over time. Where we have we expect some Q max e to the negative t over tau. Sound okay? Okay, so those are our guesses. And we could have even made them more vague. Like we could say that, hey, there'll be some constant out front. And we could say, okay, I expect a negative t times some other constant. I don't know what it is. And then what we're going to do is we're going to just take this and we're going to plug it into this equation down here and see if it works. If it works, we're good. We'll have our constant solved for, and we can just use the solution. So negative q over c minus dq dt times r equals 0. So negative q, and I'm just going to plug in like the most vague thing I have. Right? So that's just like, hey, I have a decaying exponential. There's probably some constants with it. ddt of a e to the at times r equals 0. Okay. Make sure I do this right. Negative a e to the negative at over c. For this derivative, I'm sorry, I'm going a little bit fast. I can pull the big A out front because it's a constant. So minus A. And then I'm taking the derivative of e to the negative at. So I'll take the derivative of an exponential and get an exponential back. And then I'll take the derivative of the exponent and I'll get negative A. So far, so good? Okay, good. So far, so good. Indeed. I feel like I'm going to miss. Oh, I lost my R. That's what I lost. It was like, I'm never going to get an RC out of this. Okay, looking at this, one thing we can immediately look at is the time dependence. So I have a whole bunch of stuff here, but what's the only thing in this equation that is time dependent? Where do you see the T's? With the E. Okay, so my time dependent components are that and that. And so for this solution to work, I need those time dependent components to cancel out. Because if I have a time on one side and not a time on the other, then I'm messing up. And looking at this, that minus sign will cancel out that minus sign. And so I'll be able to divide both sides. I can just do this. I can divide both sides by e to the minus at, and I can get rid of those exponentials, which is really good because otherwise I wouldn't be able to figure that. It wouldn't be a solution. And there'd be like, if I tried to plug in like q equals sine at, this wouldn't have worked because I would have a sine and a cosine, and those wouldn't cancel out. So an exponential absolutely did work, and we knew it would work because we saw this equation right here, and we said, hey, the function equals the derivative of itself. Okay, these capital A's, unfortunately, there's not much I can do with them in this. They're going to divide out. We'll talk about them later. Then I'm going to have my weird constant that was in the exponent times r equals 1 over c, or my weird constant is 1 over rc. And since I had it in the a times t, that's really t over rc, right? Okay, so even just putting in a generic constant there, I still get the right time constant out. Does that make sense? I hope so. So that means that this checks out. If you want to think about what's out front, what you do is you say Q at time equals 0 equals A e to the negative 0. And so A is really just Q at time equals 0. Does that make sense? So it's just the initial conditions, or in this case, the initial condition is the same as the maximum value. Okay, so this works for a discharging RC circuit. I will leave it as an exercise to the reader to prove that that means this current is a great equation for a discharging RC circuit that you'll get by just taking the derivative of the charge equation we just got, right? Okay. What is there anything else I needed to talk about? I think that's. I think I'm going to stop. Does anyone have any questions? Okay, I know that was kind of fast and dirty, but please feel free. Especially so look at like the last 4 or 5 problems on the homework for chapter 10. If you have any questions on those, we can go over them on Thursday. Okay. Those are all about differential equations, so be ready. And if not, we'll start on the next chapter, which will be great because it's a good chapter. Okay. Online people, are you happy?